This is the second part of the homework answers, and we're moving to the third day of homework. And the conceptual question that we're answering this time is number 23, which is applications of thermodynamics, heat pumps, and refrigerators. Now, a heat pump, number 23 states, explain why heat pumps do not work well in very cold climates as they do in milder ones. Is the same true of refrigerators? A heat pump is a heat engine running backwards. The engine transfers heat from a hot reservoir to a cold reservoir with the production of work. A heat pump transfers heat from a cold reservoir to a hot reservoir with the input of work. Heat pumps work best when the difference in temperature is small between the two reservoirs, so the colder it is outside, the greater this difference. Refrigerators, on the other hand, because most of them are inside, have a fairly constant difference in temperature, and therefore it doesn't really matter what the environmental temperature is. Number 25 states, why do refrigerators, air conditioners, heat pumps operate most cost effectively for cycles with a small temperature difference? Well, COP, which stands for coefficient of performance, is actually the 1 over the efficiency. And efficiency is work divided by the heat of the hot reservoir, or 1 minus QC over QH. Therefore, the less the difference between the two, the lower the efficiency number and the higher the COP number. And therefore, the greater the heat pump or refrigerator works. Problem number 37 states the following. What is the coefficient of performance of an ideal heat pump that has a heat transfer from cold temperature of minus 25 degrees to a hot temperature of 40 degrees? Well, as I said, efficiency is equal to 1 minus QC over QH, or you could write this 1 minus TC over TH. And so if we put that in, 1 minus 248, which is minus 25 degrees in Kelvin, have to work in Kelvin, over 313, which is 40 degrees, we get an efficiency of 0.0207. COP is 1 over the efficiency, and 1 over this number is 4.82. Number 38. The same problem. Suppose you have an ideal refrigerator that cools an environment at minus 20 degrees and has a heat transfer to another environment at 50 degrees centigrade. What is the performance? Again, 1 minus, and the first temperature is now 253 Kelvin. The second is now 323 Kelvin. And so that's going to give you a 0.217 for the efficiency. And COP here is going to be 4.67, which is this. Now 43 tells you that suppose you want to operate an ideal refrigerator with a cold temperature of minus 10, and you would like to have the coefficient of performance at 7, what would the other have to be? Well, if the coefficient of performance is 7, then the efficiency is 1 over 7, or 0.143, which is going to equal 1 minus TC over TH. And we know that TC is 263. So if we put 0.143 equals 1 minus 263 divided by TH, and if we work through this, we get a TH 307 degrees Kelvin. Now let's move back to the conceptual questions. Now these are under entropy and the second law of thermodynamics, disorder, and the unavailability of energy. And the first question is number 29. Consider a system with a certain energy content from which we wish to extract as much work as possible. Would the system's entropy be high or low? Is this orderly or disorderly, structured or uniform? Well, the entropy would need to be as low as possible, as orderly as possible, and as structured as possible. Because the more entropy is present, the more loss of work to entropy that occurs. So that we want as orderly a system as we can have. 31 says, explain how water's entropy can decrease when it freezes without violating the first law or second law of thermodynamics. Explain specifically what happens to the entropy of its surroundings. Well, that tells you how to answer the question. If the entropy of the water itself decreases, then the entropy of the surroundings has to increase and generally increases more than the entropy of the water decreases. 34. What is the change in entropy in an adiabatic process? Well, first of all, you have to know that an adiabatic process means that there is no heat transfer. Entropy can change in an adiabatic process, and it can actually change in either direction, but generally in a natural adiabatic process, it will increase. In a Carnot engine, for example, there's both an adiabatic compression, which is a decrease in entropy, and an adiabatic expansion, which represents an increase in entropy. Figure 1522 in your book. Problem number 48. On a hot summer day, 4 times 10 to the 6 joules of heat transfer into a parked car takes place, increasing its temperature from 35 to 45 degrees. What is the increase in entropy in the car due to this heat transfer alone? Well, the change in entropy is equal to Q over T. So we have 4 times 10 to the 6 joules divided by the final temperature, which is 313 degrees K. So it's going to equal to 1.28 times 10 to the 4th joules per degree K. 53 states, what is the decrease in entropy of 25 grams of water that condenses on a bathroom mirror at 35 degrees centigrade, assuming no change in temperature, given the latent heat of vaporization is 2450 kilojoules per kilogram? So delta S is going to equal minus, because when it condenses it loses heat. So that's going to equal to mass of the water times the latent heat divided by the temperature at which this occurs, which is going to be 25 grams times 2450 joules per gram, which is the same as kilojoules per kilogram, divided by 308, which is the temperature in Celsius or in Kelvin, and that's going to be minus 199 joules per degree K. So that's how much entropy is lost with that heat transfer.